So we'll go ahead and get started. My name is Vincent Batts, and this talk is containers under the hood. Really intended to not be any particular tool specific. I might hop through a few things just so you can see some of the primitives are still the same no matter what tool it is that you're using, but more getting into the different aspects of some of what containers mean to different in different parts of the implementation. So a little bit about myself. Been around in various communities for a little while now. For the last 3 years at Red Hat, it's mostly been various container-related technologies. For a couple of years was committing on upstream Docker. For the last year, it's been mostly the Open Containers Initiative. How many folks here know of or are familiar with the Open Containers Initiative? Cool, so several folks. It's a specification. It should be not very exciting for a lot of people. Ultimately, it will give the common interfaces that a lot of people have expected would exist or have already existed but haven't. So just codifying that so that people can have common interfaces to work from. If you're interested in that kind of thing, check out opencontainers.org. We're glad to have you. So specifically at Red Hat, for the years of getting started with Docker Upstream, it was for OpenShift. If you're not familiar with OpenShift, you should get familiarized with OpenShift. It's from the V2 to V3 was a whole rewrite. Now is effectively an extension of Kubernetes. So if you have anything that works with the Kubernetes API, it'll still work with OpenShift V3. And it's presently also working to adopt the Open Container Initiative. So just the highest level things that we're going to go over on this talk is getting into more of the actual capabilities and how you can explore some of those, just information about what they mean. Syscalls, copy on write. How many folks know of like more intimates of copy on write? Do you like it or dislike it? Like it, yeah. Need more options. That's fair. So most people, once they get their hands on it and get dirty or get into like a production environment, you realize perhaps that's not necessarily what we mean or what we need. But we'll get into a bit more of that. Archives, and I put this on here because it's not really a kernel construct, but it is very intimately involved, and knowing some of the natures of archives is what's going to enable us to keep building various types of orchestration frameworks and the workflows and the kind of trust frameworks we need based on what the new packaging formats are, and namespaces, and that should go in a different order there. PS, because they want us to tell everybody this, be sure to fill out the survey if you've got the app or otherwise. Make sure that you rank me where necessary. So, but first off, I mean, so containers, you've heard lots of push from various types of folks across the ecosystem of whether it should be a single application, single PID, whether it should be a whole stack, whether it should be larger than that, whether it should be like a cattle or a pet or whatever, snowflake, whatever your analogy is. How to start building this up further, whether or not it should be non-root. A lot of people for a while didn't realize just to what extent the separation of root versus non-root, who was actually calling various tools to when it actually executed your container and what context that container was being run in. How to do inheritance of like privileges and capabilities and so forth. There's some great projects bubbling up now to do more desktop applications, not just like, there's rumblings in the Windows world, but specifically on Linux to be able to handle desktop applications that are non-root. And then cats, of course, there's always some room for cats, bubble wrap. So what does container mean to you? Anybody in here, just holler out. What does the notion of container mean? Yet another layer. Fair. Portability. Oh, okay. I was about to say, still an operating system, but yeah. What'd you say? Yeah, packaging format. So several of those things. I mean, it is layers. It's turtles, and to some extent, it's a lot of turtles. But that could be for your application, or it could be for the stack. And by and large, it is packaging. And whether you're packaging the whole OS, packaging a single binary, it's a new packaging format. Some of these challenges we've solved for years. There's been debates about whether or not certain packaging systems were better than others, and then it's just gone full circle, and you have like NPM and jars, you have Ruby gems and so forth, and then people start shoving those back into Debian packages and RPM packages, and it just keeps on going. And whether it's packaging formats or it's deployment, this is what containers are turning into for some folks, but it's a next level allowing you to do this, whether you're going bento box or you're actually having a very organized fashion about it. But I just like the rainbow ones particularly. So we'll get started. Capabilities. How many folks have actively put their hands on capabilities or gotten aware of when capabilities affected your life? Yeah, hand wavy, solid. So I'll make this demo of, oh man, that is really large. So in the presentation that you can get later, there's all these are links that go out to pages, so you can maybe if I just come over here and click on this. Yeah, that's easier. So the capabilities man page, I mean, like a lot of this is readily available to you. There's various tools that allow you to go through this. The biggest time that most people become aware of capabilities is less that they were interested in it and more that they are getting an ePerm or an eAccess somewhere in their application and they have no good idea why, and it's not always SE Linux. Especially there's a number of the capabilities that you can drop, and it solves 95% of the use case. And so you see this bubble up into various tools, command lines of just like allowing one-off, addition of capabilities. Hopefully that's not directly to cap sysadmin, but the man page for capabilities, it covers pretty much all of this in depth, depending on whatever it is that you need. There's some that might be specific edge cases that let you do what you need to do. How many folks in here are more operations versus application developers? So operations first. Okay, developers. Solid. So ops guys, you should get familiar with this because you'll be troubleshooting someone's S-trace and trying to figure out what the ePerm and the eAccess came from. Developers, you should know what your application is doing. And if at all, get familiar with some of these tools so that you can drop privileges and make sure your application still works well. One of the big things that you'll see in the years coming for the container age is not just the tooling around managing and orchestrating your applications get better, involved, and change, but applications are going to start getting smarter. Your application, as a developer, as a deployer, you need to know what your application needs. You need to know what your application doesn't need. Because otherwise you're going to be deploying something, and if you haven't owned your code, if you haven't walked through what your code is importing, the calls that your code is doing, then you won't know what you do or don't need, and you'll have undefined behavior immediately. Because you'll be having code run in places where it's not been given all the capabilities, and if you can't tell somebody what capabilities it needs, you're going to have a kind of a hiccup of a time. So you should get familiarized with at least the capabilities that are out there and running your applications under fewer privileges. There's a command line tool that is in a newer version of util Linux, which is pretty widely available package. And some distributions are still not sending the set priv, but it's a very simple command line tool that you can use to not only drop and add capabilities on your on a given process, but more specifically, you can So more specifically, you can be in a shell of any kind and can ask to dump setpriv-d to dump what the current bounding set of capabilities that your PID has at that time. So you could start going through and dropping and saying, let's remove cap chom, so where you can change the owner of a file. Let's remove cap DAC override. You should almost never need that, and so on and so forth. And you can make sure that you still have the same defined behavior, whether you're going through your integration tests and otherwise. And you can drop these things one off, like on a shell. No big fancy tools. This is just like you and your shell hugging and having a good time. Like I said, setpriv is from util Linux. There's one that's actually from libcap or libcapability that's might not be on every box, but it will actually show you a little bit more, but it's pretty much the same information of what's the current bounding set, what's the current current capabilities that are even in that PID set, and the man page also gives you a lot more information about what's the difference between effective, bounding, and there's a few other verbs that they've introduced in fairly recent kernels. The other place, if you really want to get bonkers, is you can. What am I doing here? Proc self status. If you wanted to go rogue on it, you could figure out the bit masks for what your actual capabilities are. But this, when you have the ProcFS mounted into your container, even if you don't have command line tools for like libcap or setpriv or various versions, and you need to always be able to determine what capabilities are running for your PID, and you're writing an application to do this, it's always on the ProcFS for, well, self is a kind of a magic word, but otherwise, if you know the PID, the integer of the PID, you can come here and do the bit mask yourself and figure out that the current PID that you're running has the capabilities that you're going to need. So if you're doing some kind of like initialization of your application, you could check that here and make sure that you have at least what you think you need. And all that is in the proc man page. Yeah, the pseudo file system. You can come down and it'll tell you what all status is supposed to have. Anyhow, you can go to the main page yourself. Oh yeah, there we go. So that's PID status. It's got a lot of other good stuff in there, but and we'll come back to that a few times. But the proc main page is pretty helpful for that. Did any side topic, completely unrelated to anything? How many folks watched Animaniacs back in the day? Good. So almost as many developers as we have in the room. Does anybody remember Skull Face, Bony Hands? Anybody? No? Okay. He always did it would come in randomly to do a good idea, bad idea, and I loved them as a kid. So, we're paused, press B to resume. All right, so good idea. Whistling while you work. Anybody have an idea what the bad idea is? Whistling while you eat, don't do that. So we'll just keep on moving on. So syscalls, how many folks have messed with syscalls? Syscalls, good deal. So a number of syscalls. So the syscalls are a lot less fun to play with and troubleshoot. It's not nearly as straightforward as capabilities, and there's not a real straightforward way to figure out what you're bound by. The filter rules are a little interesting, even in setcomp. You can read up on the setcomp documentation. There's times when you can get into like hierarchical rules and filters, but as a PID running, the only way that you can actually figure out what syscalls are being filtered or not filtered is literally by trying them. It is not real great for, as far as an application owner or writer, to figure out that you're going into some new space and you need to make sure that your application can work just fine. Otherwise, you have to have the full integration test, and when you go to run, you run the whole stack and make sure that you're not getting undefined behavior and that you've actually written test to test, cover everything, every possible use case. The only kind of like, is the wind blowing thing that you can do is back to that proc man page. When you're inside of a container, that you can come in and check whether or not setcomp is actually running. This particular setcomp field from the PID status of the ProcFS has 3 possible states, and that's 0 is there's no setcomp policy turned on for this PID. 1 is that it's in a strict mode, but most often you'll see it as 2, that you're actually running under any kind of setcomp policy. So if you're in an environment that's running that, the most hand-wavy that you could do as a PID is just checking your PID whether or not there's filters turned on. That it could mean that your syscalls are gonna, something that somewhere in your syscalls are getting filtered. But otherwise, if it's 0, that there's no setcomp filtering happening at all. It's not real great, but I don't know how that could get much of any better at all. So, all right, another good idea, bad idea. Feeding a kitten in the park. Bad idea, feeding a kitten in the park to a bear. And I looked for images for these, but unfortunately Warner Brothers is not real forgiving on giving out the pictures of those. Namespaces. How many folks have actually put their hands on namespaces in various regards? Yeah, did you have a good time? Nope. So namespaces are actually pretty straightforward in that you can start creating a container for yourself straight away with command lines like unshare. Almost always this file is updated for whatever your kernel can do. You can already see the C group namespaces are in there. Anybody excited about C group namespaces? Anybody? Nobody? Okay. So a lot of people have been waiting on C group namespaces for a while because of the unified hierarchy that's going to be coming down. Most people are going to be running on the old V1 C groups, but as we move to V2, it'll allow for a lot of very interesting use cases as we get into like sub containers, and you want to actually unshare again and still allow proper controls of resources in like sub containers. But that's coming down the pipe. Otherwise, in namespaces themselves, you can read more about what they do in the man page, and that's the link here is to just a web man page. But this is where you can have, let's see here. You can do a pretty straightforward container. Let's make sure I have the help out. UMIP. Cool. UMIP, and we'll fork for good measure. And we'll do it straight into a chroot. It's going to go into a container file system here. Fedora, and we'll call bash. Doop. All right, so now I'm in this container that is pretty naive. You still have to do a couple of additional steps of like mounting in something like proc. No. T sysfs, none to sys. Doop, 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 doop. Dev tempfs, doop, doop. So now you've got something that, we've unshared the mount namespace, no PS. You can look into the proc and see that the only 2 PIDs that we have here is the PID that we started with, number 1, and that 25 is the ls command that was run at that time, but you're effectively in your own little mock chroot kernel, chroot container at this point. You only have the device nodes that you need. If you wanted to mount anything else into there, could do that, but it's just the kernel devtemp.fs. So yeah, I mean, like unshare command, if you have a use case where all you need is the root file system and then whatever you're going to exec into it, all the other frameworks, you could apply SELinux policy here. You could just inherit from whatever PID is calling. You could set other policies on top of this, but if you just have like a quick operation that you need to prep that root file system, this is a way that you can put your hands on a very, very rudimentary container straight away. There is information about what you can find for your PID in the proc man page here that I've referenced at this point a couple of times. Because if I go into the ProcFS for this particular PID, one of the directories that you'll find is this NS directory. And so every single PID on your host straight away is going to have this NS directory that looks like it has broken symlinks in it, but the symlinks are references held to the ProcFS inode for that particular namespace. And so this is how, if you have tooling, traditionally the tooling has just kind of walked the ProcFS to see what the PIDs presently in whatever PID namespace you're running are, and then follow those namespaces these namespace references to see which and how and who's unshared from who, what parent is unshared from what. But you can discover those references here, and it's been fairly manual up until this point. In the latest version of util Linux, there's now a command called lsns that you can see, btsync. You can see all the PIDs that are running on the host with this lsns command. And right here, you'll see that unshare that we just did. Right here, you'll see that unshare that we just did. And as impossible as it is, you can actually see that this number is different than these other numbers. So like for the mount namespace, here's your reference that's different than the shell that actually invoked it. We had a bash shell and then we unshared, so we were given a new reference, and you can keep track of that. This tool is also pretty handy in that it aggregates up how many PIDs. This is the number of processes that are under a given namespace reference. So you can see up here that this particular reference of mount namespace has 204 PIDs running in it. There's a few other options that you can get into of how and what you want to print out. Like if you only wanted to show just certain types of PIDs, just the number of processes, the PID or the parent PID of a particular namespace. It's a pretty handy tool if you have automations that's just trying to figure out where and what namespace is around. The interesting So here we have this PID that is still unshared. And if we pgrep for, what do we do, unshare? Yeah. So if I ps tree to p less to p for unshare. So you can see here that unshared, we have bash that unshares to bash. So then namespaces, another handy tool that I don't think I added on my slide. So nsenter, has anybody put their hands on nsenter? Like 3 people. So if you find yourself in this nether of trying to troubleshoot namespaces, nsenter I think is also provided by util Linux, so it's a pretty standard tool. But you can say attach to the target of that PID that we just discovered that we wanted to attach to, and I want to attach to the mount and the UTC and the IPC, and I didn't unshare net, but I want to attach to the PID. Sure. And so now I just entered into that PID, and you can, even though I might be on the hosts, well, that didn't work right, did it? Nope. I'm doing something wrong here. Traditionally, when you would ns enter into the PID, it puts you right into that PID's namespace. Well, okay. I'm doing something wrong, but I didn't write it in my notes. But NSEnter will allow you to enter into the mount namespace, or the PID's namespaces, and you can choose which PIDs, which namespaces to join, be it mount or PID or otherwise user namespace, so that you can jump into the. If the best equivalency of this is like a Docker exec, that you're attaching to those namespaces and then opening a shell in that namespace as if you were in that mount or PID namespace. All right. Questions up to this point? I should have said at the beginning, feel free to interrupt me if you have particular questions or want me to clarify something. Any questions up to this point? Nothing? Cool. All right. So good idea. Another good idea, bad idea. Playing catch with your grandpa. Bad idea. Playing catch with your grandpa. Copy on write. How many folks have used Docker and at some point realized you were using Devicemapper as your backend? How many folks did that and had a good time after that? Not many people. So Devicemapper was one of the first, well, not one of, it was the first non-AUFS driver that was added, but it is surprisingly pervasive. LVM is on all kinds of machines by default. It does a lot of things that you don't even pay attention to in your normal installer of most Linuxes, that you're going to have an LVM partition. If you do an encrypted disk, it's going to do LVM on top of it. It is very widely used for a lot of different things. The LVM thin provisioning was less often used widely, but still available. So the Docker use case gave it a lot of room to grow. The tool itself, though, if you come into any particular machine, the man page for it is right here, and it walks you through some of the various terms, some actual pretty straightforward examples of how to put your hands on doing an LVM thin provision pool. And let's see here. It's not real straightforward always how like all the commands that you're going to start running through. Where's my cursor? Jeez. All right. But let's see if we can do this real quick. So, for the sake of an example, you should never do this at home. We're going to just create a demo file. Truncate is a handy tool when you're playing with stuff like this. If you've ever found yourself DD, IF, dev0, OF, some file, block size, count, 4 megs, count, however much, like doing the math of like, I need a 20 gig image, you should do this. because DD will take a little while, even if it's only seconds, but it actually allocates the blocks on your disk. Truncate is a pretty handy file command that it sets the boundaries of the file that it can be whatever size you set, but it doesn't allocate anything on the bytes on the disk. So if you have a copy on write file system, it's not actually going through and touching the file system and doing any of those write transactions. It doesn't actually allocate anything. So we're going to get ourselves a 20 gig something to play with here. And we're going to set it up on a loopback device. VG create VG0 from dev. Nope. Jeez. Okay. So VG create L, and we'll say we'll use 50% of that free space to create a thin pool on VG0, and we'll call it thin pool. Oh, you're right. Thank you. Good job. Audience participation. So we created a logical volume now on top of our volume group, and then we're going to LV create with just like a 1 gig virtual. We're going to create a 1 gig virtual thin snapshot off of this thin pool, and we'll call it volume 1. Cannot. There's something about typing in front of people that your competency goes down by a significant marker. All right, so now we're just going to make a directory of vol1 and mount VG0 vol1 to vol1. Oh. So the other interesting thing, and you'll see this more in the next example with both overlay and ButterFS, that are managed. They rely on other aspects of the file system. ButterFS itself is the file system. The big thing to notice about the Devicemapper, there are certain features that are more supported on ext4 and XFS, but it itself is just a block-for-block replication. So now that we've actually created a thin device of volume 1, it itself is not ready for anything. So it's just an empty block device, effectively. So now we've formatted it, and we'll put something into a file. So now when we cat that file, you can see that that's the time that we just made for ourselves. And now we're going to go through, even while that thing is still connected and set up, and we're going to make a snapshot from that volume, and we'll call it name vol1 snap1 from VG vol0, and we'll make something called snap1. Now VG0 vol1 snap1. So you can see that it's the same thing, and we can come in and echo date into file 2 and see that it didn't change that at all. So it just only changed the blocks and bytes that are necessary. To further that example, if this had been a very large file, like spanning multiple blocks within the thin pool itself, it would have only copied up and changed the pieces necessary. It wouldn't have done a whole copy up of the entire file. In this example, only 2 bytes are different. but which is probably still within the same block, but it only copies up the blocks that have actually changed. So behind the scenes, if like in Docker, if you are using, regardless of how you're using it, this is effectively how it's any given image that starts, and then every layer that's done on top of it is just taking snapshots of that and mounting them read-only from the block device that it's set up for itself. So if that's ever seemed mystical, this is really all that's happening behind the scenes. If you look at the commands, it ends up being a fair amount of commands, and you have to still unmount all of them and disactivate the group and handle the locking, because if you have more than one PID doing some of these operations at the same time, locking can get into a little bit of a nightmare. But that's how this is done.
So when you say that this is doing, this is what Docker, for example, is doing underneath, is this call into the kernel of the Devicemapper infrastructure under LV3, under the LV3? Are those exactly using those exact same calls?
I sure wish it was. Boy, that would have made a lot of our lives a lot easier. It's actually going through more like if you were to do DM setup, and it's talking directly through more the kernel API. So by and large, the Devicemapper driver that's in Docker has wholly re-implemented whole swaths of what the LV command line toolset does. Yeah. So there's lots of dependencies and orderings and making sure that you've passed certain cookies through the kernel to make sure that certain transactions block before, because the LVM tool set has had to work around a lot of those things, but has done it such that it can make sure that there's certain transactions that need to be blocked and done in certain orders, and all that's been re-implemented in the Docker Devicemapper graph driver. It would have made everybody's life a lot easier had we just shelled out, but then it would have made a dependency that you apt-get install additional command line tools that might not have been everywhere, whereas we knew that it would be in the kernel.
So, Docker, for example, is doing effectively the same thing as LV3.
Yes, yeah.
It's doing it using a re-implementation of the same set of system calls.
Yes. Yep. And having to handle a lot of the edge cases that LVM's already covered, the command line tools. Any other questions about that? Cool. All right. So then one of the other ones, how many people use ButterFS ever? Production? I personally like ButterFS a lot, but it is not largely trusted. That's fine. ButterFS, and if you ever do this truncate command, I'm still working on that same 20 gig demo image right there. You can actually make ButterFS straight onto, you could just straight MKFS to the file itself. Moved to S1. Ball one. Demo. All right, so now we'll just mount. Oh. All right, so we're going to mount -o to do on loopback this file that we've just created, and we're going to mount it to demo. So ButterFS by default, if you're ever doing this, regardless of container or not, it puts you into a root context on the file system that you've mounted. So if you want to start doing operations that you can snapshot or use some of the other sophisticated features, you actually have to create for yourself a sub-volume to begin with. So you might see me from time to time do some short abbreviations here. The command line tool lets you give partials on the sub-commands. But ButterFS subvolume, and this is where you can actually make for yourself a subvolume. So we're going to ButterFS create volume 1, and we'll go into volume, we'll we'll make a file into here, and then we can immediately do a ButterFS sub snapshot from volume 1, and we'll call it, vol1 snap1 cat the files, and you can see that it's the same file. Date into vol1 snap1 file, and you can see that just the bits necessary, or only the bits that have changed in that 28 seconds is the only things that have changed. ButterFS also only does a block for block copy up. So had this been a very large file and you only changed 1 byte of it or 2 bytes of it, only the blocks that those are spanning would get copied up. The rest of the file would still be deduplicated within the file system. Something I didn't touch on with Devicemapper LVM, but is true for both Devicemapper LVM and ButterFS and a few of the other ones. I think including even ZFS, if anybody's played with that, is that even though you can see that I'm on, I've just mounted a single block device, or super block device, dev loop 1 in this case, or whatever it was, to this directory that I'm standing in. In your mind, you might say, I'm on a device, but now that I've created this subvolume and a snapshot of the subvolume, something subtle here is the so if you ever stat a particular directory and you see here the device information right there, has that, anybody in the room, has that device piece right here, well, including the inode, has that ever meant anything to anybody in this room? Yes or no? A couple of people, yes. It should, and if you're getting into nuances of sometimes performance and density testing and all kinds of stuff, especially in the container world, if you're having to deal with copy on writes, that should matter to you. And the reason that that should matter to you is because now I'm going to stat both the file that I created and the snapshot of the file that I created. And you'll see that now that is different than that is different than that. Oddly, the original file and the snapshot of the file, they have the same inode, but they have a different device ID. In the kernel, it makes a lot of sense for this to be the case, and it's how it gets managed, and there's lots of contexts that this needs to be different. For SE Linux or AppArm or whatnot, it's the way that they can get a hold of an inode and figure out what device it's a part of and the contexts and all this kind of stuff. But one little nuance of it for a lot of people means that page caching of the applications that you're running goes almost sideways. So now if you had the exact same application, say it's a Ruby stack, and you have the exact same Ruby stack, and the only thing that's different is the last mile. You have a Sinatra application, and it's 30 lines, and it does a get and a post and whatever. It's like a text file. But up until that point, it's loaded libc and LDS Linux SO, and it's Ruby and the whole shebang. It's got all this stuff that the kernel has loaded. These these binaries that are immutable, and you think you're running 10 of the exact same stack. If those things are different, your kernel has cached 10 instances of Ruby all the way down to libc for each one of those containers, period. The page caching depends on that information inside the kernel. KSM, I'll have to go back and put my hands on it. I'm blanking on that right now. Yeah. I'll have to put my hands on it. I can't answer that for you right now. It's nice and it's magical, especially for ButterFS, because you can manage these, and ButterFS allows you to do some other really interesting things where now I'm going to step out of that mount that I have going, and I'm going to make myself, an entirely new directory for these two things. And I'm going to mount now the subvolume of, what did I call it? Vol1 from dev loop 1 into this new directory. Oh. And I'm going to mount the snapshot to S2. Oh, for crying out loud. So if you look here, I've got the original directory that we mounted once, and you can see that it's coming from demo img, and I'm mounting v1 and the volume 1 and the snapshot of that volume straight back to the super block, as it were, but I'm going straight into that subdirectory. I don't even see the whole tree. So if I go into this v1, the only thing I'm going to see is file. And if I likewise, if I go into the snapshot, so it could allow you to manage those instances wholly separate, and they're not even on the whole mounted ButterFS file system. Some things still get a little leaky if you're trying to figure out what all paths are in here. So now I'm in the mounted subvolume, but I can actually see that there is another subvolume that existed called vol1. So this is where it'd be a case that if you were running containers in this environment, that you want them to be not root, not have access to do ioctls, but because you'd be leaking information about the file system. But you could actually mount somebody a file system straight away. Questions about that? I'll move on quickly, but another fun thing is that for what was like 15 commands and a lot of cleanup, and Devicemapper is typically only about 5 commands in ButterFS, and it cleans up nicely. Yeah, so. Yeah, okay. So lastly, on the copy on writes that I'm going to cover here is overlayFS. How many folks have put their hands on overlayFS? Nobody. So overlayFS is one of the more recent UnionFSs that's been pushed into the kernel, since there was an effort for UnionFS for a long time that never fully got merged into the kernel. Most people carried it if they wanted to do like live disks and some other interesting use cases to do like a union. Whereas overlayFS was actually merged into the kernel. There's a driver for it if you use Docker. It serves a lot of use cases, and in the page caching, it actually fixes some of those use cases. So here in this very simple little script, for the sake of convenience, I'm just going to make a couple of directories here. You can do a mount-t for the type of overlay, and then most of it is all done in the options that you pass. It has to have like a working directory. You can figure out where the upper and lower directories are. And so when we run bash -6, that you can see I touched a file, I added a new file. You can even go back and remove the files, and the upper directory is storing where the action happened and the consistency across where what you've touched and one doesn't overlay to the other. Some drawbacks of overlayFS is that due to some of the design decisions that had to happen for it to happen for this implementation, and it shares the device, major, minor device numbers. If I do the file here and you can see that no matter what, even if the inode has changed in a couple of these, all right here, this inode is the same as that inode. That major minor device is the same as that major minor device. For some of the design decisions that happened so that you could actually have multiple copies of the same file system and have this ephemeral feeling, but it still be the same major minor device and same inodes for files that haven't actually changed. overlayFS is not entirely POSIX compliant. And there are certain things that are still edge cases where we're working through, like if you have an application workflow that will open a file handle for read-write, or for read-only, it won't do a copy up. So you might open something to read from it, and then at a later point you open a read-write file handle. As soon as the kernel gets that read-write, write access to the file, it copies up the new file, but you still got the file handle to the old inode, which is still completely valid. So you might actually start writing something, and then you start seeking around over here and rereading, and it's different content. So you can find yourself in some very bizarre edge cases, and this is why when it first rolled out, some tools like some of the package managers were getting like invalid lock errors, and they were getting invalid reads because they were doing this kind of workflow, which is a not terribly uncommon workflow. As far as copy and writes go, overlayFS, as soon as you do a write or an append or whatever truncate operation, it is not a block replicating copy on write. It copies up the whole file. So if you're dealing with big files, if you add 1 byte to the end of a 100 meg file, it will copy up 100 megs every time. So know your use cases, and you might have situations where you effectively want it to be read-only, but you want to run 10 instances, and it's not going to get into crazy shenanigans. You might find more efficiency in overlayFS. ButterFS is really fast. You might find situations where that works for you. Same for Devicemapper or some of the other ones, but you need to, if you're using and put your hands on these, or rather you don't know that you're using these and putting your hands on these, you should get familiar with your workflow and the benefits and drawbacks of all the different options there. All right. I'm gonna move on. We got like 10 minutes left. So good idea, being served breakfast in bed. Bad idea, being served tennis balls in bed. Ha! All right, so file system magic. Who's heard of shared subtree propagation? Shared subtree propagation. I can guarantee you've all been affected by it. I'm not actually gonna demo this one at all. I have left access here. It's in the kernel file system documentation, but you will see this in various Docker mount, like for volumes operations, whether or not you want something to be master, shared, slave, or private. It's in systemd unit files. You can set whether or not you want certain mounts to be shared and private and slave. For anybody who has actually put their hands on this, there are absolute use cases that it makes sense. And every single time, even if you know what you're doing, you will find yourself off in a no man's land of where and what context you are mounting something so that you can even see the files within the directory. And they actually show you on this web page, on the shared subtree text, and just as an FYI, you will likely have seen this bubbled up in various documentation. This should give you just a hint of awareness of what it means. But largely, if you are in a slave mount, that means that anything that when you unshare your mount namespace, so not shared subtree stuff aside, when you unshare your mount namespace, you could actually perform mounts. You could do some of the stuff that I was just showing you, And as soon as the PID that you have done those mounts in exits, there's no more references left to those mounts, the kernel will reap them. It's effectively unmounting, doing a U-mount of those because the kernel knows there's no PID alive that holds any references to those mounts. There's various PIDs that are on any given host right now, like the cups daemon, the printer daemon. As soon as it starts, it unshares the mount namespace and does some other mount operations. When other PIDs, if you're acting and doing mounts in like PID 1, for instance, or top level of the mount namespace, anything that you do and do a mount of, if somebody else unshares during that time, they might hold a reference to your mount in their unshared mount namespace. So then when you go to remove a device or something like that, and it says like permission denied, the device is busy. And a lot of people saw this with Devicemapper because Devicemapper is constantly creating a new snapshot. It would actually create a device, and then when that container ends, it needs to remove the device, and it goes to remove the device, but if during that time somebody has unshared the mount namespace, there's a reference somewhere in the kernel, even if you can't see it from the top level now, held to that device because somebody has unshared the mount namespace and it has a mount to that device. So the kernel says, that device can't go away right now, it's busy. You layer on top of that already kind of mount namespace and references to mounts and which direction the data can go. When you do a mount, a shared subtree propagation mount, slaves will inherit mount information from their parent. So if I do a new mount, the slave can become aware of it, but if in that slave's space they do a mount, it will not propagate back up. So they might actually mount something and touch files in it, and it will show up there, but it won't show back up to the parent. Private means completely there's no bidirectional pass of whether the data, like any mounts that happen that the master sees it or vice versa. And shared means that well, shared has, you can read the documentation, it's a little fuzzy, but shared kind of allows for bidirectional, but there's still a relationship there. Unbindable literally means you can't bind the device. So sometimes if you're trying to do a volume mount of a device in, it just wouldn't show up at all. And unless you know what this is, you have to go read the mount info, the proc mount info for a file or a PID to see if there's any shared subtree propagation going on. The examples on this kernel documentation will walk through some of the different hierarchies and like, case in point, like I did this and files aren't showing up. I can see it on the host, but I can't see it in the sub mount. And there's a whole matrix of like, this will work, that won't work. This and this will do that, and this will do this other thing, and it gets wild. But if you ever find yourself in this deep, dark place, grab a cup of coffee and come to this documentation page. I'm not going to allow any questions on that because it is magic. Doop, doop, doop. I'm almost done. So, ordering a chili dog to go. Bad idea ordering a chili dog that makes you go. So, tar archives, I'm not even going to have time to get into this, but tar archives are a stream-based format. They've been around for way too long, painfully long, but it is literally an unordered stream of 512K blocks, completely unordered, and there's only a certain amount of information you can fit in any given header. Largely, they are great and horrible at the same time, but to work around that, we've actually had to get pretty creative on some tooling. At this point, there's actually a library tooling called tar split, and it's a command line tool as well that I've written. If you're interested in this, or if you just find yourself wanting to be bemused by old technologies thought of in a new way, I would love and welcome your feedback on this tool. But due to the fact that pretty much every container tool out there right now is shipping around the images in tar archives, but they're also needing content addressability, deterministic content addressability and hashing, but you don't want to keep around a 2 gig image that you just downloaded and extract it just for the sake of having that predictable content addressability. So both Rocket and Docker at this point are using this particular library to do a pristine disassembly and reassembly of tar archives. It's kind of fun in a very demented sort of way, but it allows you to be able to split up a file that might be, like here's an example. It's a 1.4 gig image that you could do the disassembly of and basically build yourself a ref log to play it back. And so then you can extract the archive and do whatever you need to do, like in the container sense, it will pull it down and lay it onto the graph driver. And then when it goes to push it back up, it will, the stashed aside ref log for this 1.4 gig image is only 2.2 megs. So your escrow is only 2.2 megs instead of having to keep the 1.4 gig image sitting right next to the extracted, however much it extracts to, due to compression. So it is interesting and awful at the same time, but I welcome any improvements or feedback that you have on that. The format is not particularly exciting, but the most exciting thing about it is the awful thing that the GNU tar format has done to accommodate like extended attributes and all kinds of different like long file names. They keep some people up at night. All right, dressing up for Halloween as a pirate, bad idea. Dressing up for Halloween as a piñata. And that is it for me. Any questions? We're right at, are we right at time? We're right at time. Any particular questions?